kind of a daunting task when I look at the specializations of most of you, where the closest most of you probably get to agriculture is Safeway. I have to, in one talk, leap beyond the kind of agriculture that goes on in Iowa to the kind that goes on in the vast majority of the world, and see what impacts both PCR and the future instrumentation that this will give rise to can have on that, and how we can learn some lessons from it. I'm going to start by going back to some basics that most of you, and in fact also myself, have viewed as being our terra firma for science, and that's the model system. Now, you're probably all familiar with the concept of the model system since you use it on a daily basis. We're restricted in our approach in reductionism in science, which I'm not saying is a pejorative, to trying to get as simple a system as possible with a few characteristic properties. And this may seem very obvious to you, but I'm going to go over them anyway so I can contrast this with the real world, which nominally we're interested in studying. Now, we try to find a system that's completely homogeneous, if we possibly can, that's site independent. So an experiment done here at Cold Spring Harbor will work in Beijing. We try to eliminate as many variables as possible, controlling the situation, and extraneous influences are to be avoided. Mood of the investigator, phase of the moon. Oh boy, everybody needs coffee. Reproducible, very important issue. I mean, if you can't reproduce an experiment, is it really even an experiment? And finally, in model systems work, there's an extreme value on incremental logic, the kind of logic where we can codify each of the steps. The idea of an intuitive leap is quite useful personally to each of us, and yet we cannot codify that intuitive leap, and so inappropriate. It's in the realm of belief, as Carrie would have said. Now let's contrast that with something that's a really remarkable circumstance, and that is traditional farming systems. If you look out in the real world, for the last 5,000 or 10,000 years since humankind has been seriously into agriculture, almost by definition, in many places, sustainable agricultural systems have been developed. Now, they're sustainable by definition because for many thousands of years, people have lived on the same pieces of land in many circumstances, not all. Now, what's characteristic of these traditional farming systems is that they're highly heterogeneous. They're absolutely site-dependent. Even now in these traditional communities, no two farmers' plots are the same and will be performed the same. In fact, you'll find the exact same problem in Idaho and Iowa. They're highly complex and highly diverse, and not just in terms of the gross biota of plants, but in fact in the microbiota, where the complexity and diversity are staggering. Variables are a natural part of farming. I mean, you can't say if only we had good weather, or if only this, or if only that. It just doesn't work. There's no partial credit. In agriculture, it's all or none. Irreproducible and risk-prone is a really serious issue with traditional farming systems, and so consequently, exigency buffering mechanisms have been developed. That is, ways of buffering risk and buffering the reproducibility by alternative systems. And most important, there's a very overt value on intuition and difficult to codify knowledge, which is often called indigenous knowledge, but that misses the point. It's a powerful logical tool that deals with highly complex issues. All of us recognize it in ourselves and our colleagues, but we rarely codify it. Now, how does this contrast with modern agriculture, the Safeway kind? What we have done over the last 50 or so years, and even before that, is develop what I call green revolution farming systems, or industrialized farming systems that are highly centralized. And they have, again, like the model system, point by point, striven to turn the environment, a complex biotic environment, into a model system. We have tried to make farming homogeneous. Often you'll see only one crop grown over 10, 20, 30,000 hectares of land. Hectares, 100 meters on a side. Site independent. That is that in principle, we want to see similar grain yields, for instance, between Saskatchewan and another province, or we want to see between Kansas and Nebraska, similar yields, similar performances. And very often the plant breeding community will try to breed varieties that will perform fairly universally between fairly diverse cropping zones. Minimize extraneous influences and eliminate variables. Oh, this is called pesticides. This is called fertilizer. Basically, as soon as you have variables in your soil, as soon as you have variables in your ecosystems, you get rid of them. So modern industrialized or green revolution farming systems eliminate the biotic buffering. And I'll come back to this extensively at the end. They strive to be as reproducible as possible and use, for instance, social mechanisms like price supports and subsidies to ensure that that's the case. And again, we're trying to increasingly put a value on incremental logic. The problem is incremental logic works only when there's measurable increments. And when you talk about a complex biotic system, this is extremely difficult to comprehend. And I'm going to, again, focus on that for the rest of the talk. What we're facing in most of the world is enormous crisis in agriculture and the environment, and most of us in the industrialized world don't see it. We almost never experience this, and so consequently to us it's something you occasionally read about in the back page of Science or something, but it's not a real issue. But out there it is. Environmental degradation, loss of soils, loss of livelihoods, food insecurities, they're staggeringly important. And when I'm told that the largest cause of mental retardation is Fragile X, I would question whether in fact the largest cause is malnutrition, which is vastly common in the third world. Now, the real problem, of course, is not that these are problems. These are symptoms. The problem is the way we go about environmental and agricultural management. Basically, we uncouple people who have a vested interest and a vested local intuition and knowledge from the ability to solve problems. And that's basically us. We're priests. I mean, we're trying to do a good job. We're trying to solve problems for other people. But when that happens, we uncouple them from the process. Their inertia, basically, to do so. We also have a problem that every ministry in the government of any world has an environment ministry and an agriculture ministry, and they're almost never the same. We treat like the environment is separate than agriculture, and yet virtually all arable land in the world is given over to agriculture. When I say virtually all, it's a very large proportion. A major limitation, how do we approach these problems and make the next jump to localized, decentralized solutions, is the tools we have. And this is where we're starting to feed into the issue of PCR. The tools that we must develop must address the problem where it exists. We cannot always reduce complex ecosystem issues into simulacra of the real world. We have to actually address it there. Also, the tools must function under the social, economic, and very importantly, the personal constraints of the ultimate users. That is, just like Toyota develops a car to work for a driver, not for a mechanic. And if it's a successful car, it never sees a mechanic again. That's what we have to aim for in tool development. So these tools must work for people who aren't the designers of the tools. This seems very obvious, but in fact in science, it's scientists who use scientific tools by and large, and it's next for agriculture to move it into the farming communities and the forestry and fishing communities. So molecular biology, and for this you could substitute PCR, but I didn't want to make a new slide, now allows biological tools to be developed to be used by those experiencing problems where the problems occur.